Welcome. In this video, we're going to discuss a new technique referred to as DefectHunter for autonomously detecting software vulnerabilities using deep learning. The technique is thoroughly described in the paper DefectHunter, a novel LLM-driven Boosted-Conformer-based code vulnerability detection mechanism. Cybersecurity has become an increasingly important concept in the last decades, and even more in the last years. Computer systems are more and more ubiquitous, and everything's connected. The number of disclosed vulnerabilities has steadily increased to absurd amounts. And this makes sense. Software and hardware are more complex than ever, providing terrific features. Hardware needs to follow, but that sometimes come with regressions, such as the dreaded Meltdown and Spectre CPU vulnerabilities. Vulnerabilities can happen at several layers, most notably hardware and software. We are only going to focus on the software part, though. Let's have a look at some common software vulnerabilities. A race condition occurs when the behavior of a software system depends on the sequence or timing of uncontrollable events, leading to unpredictable or erroneous behavior when these events do not occur in the order the programmer intended. Improper handling of exceptional conditions refers to the failure of a program to properly respond to unexpected or erroneous situations, which can result in crashes, incorrect results, or vulnerabilities. Null pointer dereference happens when a program attempts to read or write to memory using a pointer that is set to null, causing a crash or undefined behavior because there is no valid object at that address. Reliance on undefined behavior occurs when a program's logic depends on aspects of the language that are not specified by the language standard, leading to unpredictable results across different compilers, platforms, or even program runs. In this example, we're delving into the buffer overflow vulnerability caused by improper bounds checking. The function vulnerable function is designed to copy a string into a buffer that can hold only 10 characters. However, it doesn't check the length of the input. When a longer input is provided, as seen in main, the function tries to copy this input into the buffer, exceeding its capacity. This leads to a buffer overflow, which can corrupt nearby memory and potentially lead to arbitrary code execution. This is a textbook case of why bounds checking is critical in secure programming. Here's another example of buffer overflow. The function is designed to allocate an image buffer. The buffer size variable is calculated based on the image's width and height, but crucially, it fails to account for the number of color channels. Consequently, if the image has more than one channel, which is common with color images, the allocated buffer will be too small. This oversight can lead to a buffer overflow when more data is written to image buffer than it can hold, potentially allowing attackers to execute arbitrary code or cause a system crash. It's a common and dangerous security flaw that every developer needs to be vigilant against. This code snippet illustrates a common oversight in parameter validation. The function processImagePacket is vulnerable because it does not verify whether the packet pointer is null. Without this check, if a null pointer is passed to the function, it could lead to a runtime error or undefined behavior which attackers could exploit. Proper parameter validation is essential to ensure that the function operates on valid inputs, preventing potential security vulnerabilities and ensuring the stability of the program. These examples are meant to illustrate common vulnerabilities. In reality, vulnerabilities can be much harder to detect as the programs become much more complex. The main detection technique, which we'll discuss in a moment, is capable of tackling much more intricate problems. In this context, the Blue Team, cybersecurity researchers, have been looking for ways to detect vulnerabilities before they ever happen. Let's have a look at the two main categories of analysis: dynamic and static. Dynamic application security testing is what people usually have in mind when thinking about software security. It is a method of assessing the security of a web application in real time by actively testing its running code for vulnerabilities. DAST works by simulating attacks and analyzing the application's response to identify potential weaknesses, such as input validation errors, authentication issues, and other security vulnerabilities. However, its focus on the external behavior during runtime means that it may not provide a comprehensive view of the internal code structure. It may not thoroughly examine all features of an application, especially those that are not regularly accessed. Consequently, certain functionalities may escape scrutiny. In contrast, static analysis delves into the heart of an application by scrutinizing its source code or binaries before execution. This method provides a thorough examination of the codebase, uncovering potential vulnerabilities at a static level. It operates early in the development lifecycle, offering developers insights into issues before the application reaches a deployed state. Both SAST and DAST prevent vulnerability, but with an ideal tool, SAST could be used to find any potential vulnerability as soon as the code is written. For the rest of the video, we will focus on static analysis. Traditional static analysis consists in looking for common patterns. These patterns are hard-coded. The tool is not improving by itself, but only when developers work on it. One of the most common examples is to perform null analysis. In simple situations, it is easy to detect usage of a variable set to null. It is great at local scope, or to recognize mistakes junior developers often commit, but it usually fails at a larger scale. That's why there have been attempts at other approaches. In machine learning, there is VCC Finder, based on support vector machines. To put it simply, it tries to find the equation of a line to separate positive and negative samples. More recently, other deep learning approaches such as CodeT5 and the famous large language model GPT-4 have also been applied, with incremental improvements through each step of the way. These comes with a heavy price though, as running a large model is expensive. With this in mind, let's now take a deep dive into DefectHunter. Among the detection approaches we saw earlier, DefectHunter uses static analysis. Contrary to dynamic approaches, DefectHunter makes conclusions purely based on semantic analysis of the program through different representations. The research paper positions deep learning as a potent alternative to traditional machine learning for vulnerability detection, especially due to its capability to handle complex datasets and capture intricate relationships. While large language models, LLMs, like GPT-4, enhance semantic processing, they can be limited by their resource-intensive nature. Deep learning models, like the one introduced in DefectHunter, strike a balance by providing strong predictive performance with greater efficiency and lower operational costs compared to LLMs. DefectHunter is a model that artfully combines established methodologies to create a robust system for detecting code vulnerabilities. This synergy of pre-existing components and techniques allows DefectHunter to efficiently and effectively pinpoint potential security issues in software. Here's an overview of the existing methods that DefectHunter synthesizes to revolutionize vulnerability detection. It utilizes a pre-trained model for generating vector representations of code, capturing the semantic nuances essential for understanding complex code syntax and structure. TreeSitter provides a broader vision of code semantics by converting source code into a structured format that is easier for models to interpret, enhancing the model's comprehension capabilities. The conformer mechanism merges the best aspects of the transformer architecture and convolutional neural networks, allowing DefectHunter to grasp both the minute details and the broader context within the code. Finally, it applies a tweak to the attention mechanism that reduces noise by modifying the attention calculation, ensuring that only relevant information influences the model's predictions. Each component is key to the DefectHunter approach, working in concert to create a more precise and efficient tool for identifying potential security vulnerabilities in software. We're going to dive deeper into these methods in isolation when analyzing the overall architecture. With that in mind, let's take a look at the overall architecture of DefectHunter. The starting point of the analysis is a sample of code. The code sample is transformed into different types of graphs: abstract syntax tree, AST, data flow graph, DFG, and control flow graph, CFG, each providing a unique perspective on the code's structure and logic. TreeSitter, a crucial component in DefectHunter, is utilized to parse source code, converting it into abstract syntax trees, ASTs. These trees provide a hierarchical model of the code's syntactic structure, enabling a more nuanced and detailed understanding of the code's logic. The abstract syntax tree represents the syntax of the program in question in a hierarchical fashion. Compared to the other two, it is the representation which is closest to the original source code. The AST provides a detailed blueprint of the hierarchical structure of the source code, representing the syntactic constructs of the programming language. It serves as a starting point for more advanced structural analysis. Next up, the control flow graph and data flow graph are obtained from the abstract syntax tree. The control flow graph is based off of the abstract syntax tree. It focuses on the presence of conditional statements and loops. Anything that deviates from linear execution will be clearly visible from this point of view. To generate the CFG, DefectHunter utilizes the AST to trace the flow of control within the code. By traversing the AST nodes, DefectHunter identifies the points where control is transferred, such as loops, conditionals, and branches. Each node in the CFG corresponds to these control points or blocks of straight-line code, and the edges represent the flow between them. The data flow graph focuses on the dependencies and relationships between different variables and data elements present inside the program. The DFG is extracted by analyzing how data is used and modified throughout the code. The AST is traversed to locate nodes representing variable declarations, assignments, and usages. The DFG is constructed by linking these nodes with edges that represent the dependencies and the flow of data between them. These three representations combined provide downstream components with more semantic information about the code. But we're not done yet. Additionally, code sequence embedding, CSE, is used for semantic representation. DefectHunter employs UniX Coder, a cross-modal pre-trained model, to create code sequence embeddings for capturing the semantic features of source code. However, initial tokenization challenges led to inaccurate embeddings. To resolve this, the Natural Language Toolkit, NLTK, was used to refine the tokenization process, and a specialized word list was created to ensure the accuracy of tokens. This approach allows UniX Coder to generate precise code sequence embeddings with a max length configuration to support up to 768 input tokens, crucial for the model's performance in vulnerability detection. Each graph representation is then independently processed through a series of conformer blocks. These blocks are designed to capture and integrate both local and global contextual information within the code. We're going to get back on this to dive deeper into what's inside a conformer block. The output of each conformer block is flattened, turning the structured data into a format suitable for further processing. The flattened outputs are concatenated to create a single, unified feature vector that combines information from structural and semantic representations of the code. This unified feature vector is then passed through a multi-layer perceptron. The MLP is a type of neural network that can learn a nonlinear function between the input and output, which is essential for distinguishing between vulnerable and non-vulnerable code patterns. Finally, the MLP output is fed into a softmax function, which classifies the input as either containing a vulnerability or not. The softmax function outputs probabilities, effectively assigning a likelihood to the potential presence of vulnerabilities in the code snippet. Now let's go back and take a look at what's inside a conformer block. Conformer combines convolutional neural network, CNN, and self-attention mechanisms, offering an efficient way to model both local and global sequence dependencies. It includes a convolutional module for capturing local context and feature patterns, and self-attention modules for long-range dependencies within the code sequence. Traditional transformers struggle with long sequences due to quadratic computational complexity. The conformer addresses this by effectively managing extended sequences and maintaining performance even with complex input data. Here's the architecture of the conformer blocks seen prior. Let's break down each component. Let's start with position embedding. This is the initial layer of the conformer block, where the input sequence is combined with positional embeddings. Positional embeddings are crucial as they enable the model to maintain the order of the sequence, ensuring that the positional information of tokens in a sequence is retained. Both before and after the multi-head attention, there are feed-forward modules. These consist of linear layers that introduce non-linearity into the network, allowing it to capture complex relationships between the features extracted by the attention mechanism. Unique to the conformer architecture, the convolution module is included to capture local dependencies. Conventional transformers do not have this feature. The convolutional layers can identify patterns within small regions of the input sequence, enhancing the model's understanding of the local context. Following the convolution module, the sequence is passed through the multi-head attention mechanism. This allows the model to focus on different parts of the sequence simultaneously, capturing various contextual relationships within the data. Finally, layer normalization is applied following the final feed-forward module. This process normalizes the inputs across the features for each layer, stabilizing the learning and allowing for faster training. The plus symbols in the diagram represent addition operations, which are part of the residual connections. These connections allow the input of each module to be added to its output, helping to mitigate the vanishing gradient problem and enabling the training of deeper models. Each of these components plays a vital role in the conformer block's ability to process sequences. The conformer block is adept at capturing a blend of local and global contextual information, making it particularly effective for tasks like vulnerability detection in code. The architecture is designed to overcome some of the limitations of the transformer architecture, particularly in handling longer sequences by combining convolutional layers with self-attention mechanisms. Let's go back to the multi-head attention component for a moment to discuss another improvement made. In multi-head attention mechanisms, forcing every head to contribute can lead to excessive noise, affecting model performance. DefectHunter introduces an innovative solution to this problem. The attention mechanism adjustment is inspired by Evan Miller's concept of attention is off by one, where he finds that unnecessary head contributions can lead to inaccuracies. He proposes a fix which is used by DefectHunter. By modifying the softmax function used in the attention calculation, DefectHunter adds 1 to the denominator, which helps in maintaining a positive derivative and ensures a bounded output, stabilizing the attention mechanism. Here is the change in the attention formula, which ensures that attention heads only adds valuable information to the model's output. This small but crucial change significantly enhances the model's accuracy by preventing the dilution of attention with irrelevant information, leading to a more precise vulnerability detection process. Now let's examine the results from the paper. DefectHunter consistently performs at or above the level of the best methods in most cases. It significantly surpasses the average in all scenarios, demonstrating its robustness and reliability in vulnerability detection. This superior performance highlights its advanced capabilities in accurately identifying and addressing security issues in software systems. The analysis reinforces the previous findings. Overall, DefectHunter exhibits superior effectiveness compared to other methods. Its comprehensive approach to identifying vulnerabilities ensures a more secure and reliable software environment, proving its excellence in the field of cybersecurity. Removing certain components from DefectHunter results in decreased effectiveness. Particularly, omitting the language model leads to the most significant performance drop. Similarly, excluding the conformer component can yield poor outcomes in certain scenarios, underscoring the importance of each element in the model. There are some technical limitations, though. Control flow graphs represent all possible paths a program can take during execution. However, they face challenges. Structural complexity in modern complex architectures leads to highly intricate CFGs, complicating full analysis. Code dynamism isn't effectively captured by static CFGs, missing conditional executions and indirect function calls. Data flow graphs illustrate data manipulation and transfer in code, yet they have limitations: incomplete abstraction in high-level languages and missed indirect or nonlinear dependencies. These limitations complicate vulnerability analysis, especially for context-dependent or subtly hidden vulnerabilities, increasing risks of false negatives where real vulnerabilities remain undetected. False negatives are critically problematic, as highlighted by the study. They are more severe than false positives, as they allow actual vulnerabilities to go unnoticed. This could potentially link to the limitations in CFG and DFG analyses. Understanding and addressing these risks are crucial for effective vulnerability detection, emphasizing the need for comprehensive and accurate analysis methods like DefectHunter. Thank you for your time. If you have any questions, feel free to drop a comment